I am personally a believer in determinism, not least because I think stochasticity is, in practice, noise is very important. It's important in weather and climate models. It's important in the brain. So at a kind of practical level, noise is important. But at a fundamental level, if you're really going back to absolute fundamentals, I think noise and stochasticity make no sense whatsoever. And I think ultimately the world has to be deterministic because I can't see anything else making any sense.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 162. And this episode is with Tim Palmer, who is Royal Society Research Professor in Climate Physics at the University of Oxford, where he is a Senior Fellow at the Oxford Martin Institute and a Professorial Fellow at Jesus College. And although Tim's training was in theoretical physics, and we talk a lot about theoretical physics and the foundations of physics, he works on the predictability and dynamics of weather and climate, including extreme events, and is well known within the field for developing probabilistic ensemble forecasting techniques, which, of course, we get into. But for the most part, in this episode, Tim and I discuss his recent book, The Primacy of Doubt, From Quantum Physics to Climate Change, how the science of uncertainty can help us understand our chaotic world. More particularly, and this doesn't have so much to do with the primacy of doubt, we talk about black holes and the holographic principle, the foundations of quantum mechanics, and then enter the primacy of doubt, meteorology, chaos theory, consciousness and free will, and the problem of climate change. So there's a link to the primacy of doubt in the description, and likes, comments, subscribes, reviews, follows, all these things are so helpful. So please do that if you haven't, or even if you already have. And now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Tim. I know that you did your doctorate in theoretical physics and specifically on energy and momentum in general relativity, but since then you've been best known for working in meteorology. And before reading The Primacy of Doubt, I'd never really thought about how the two might be connected, though of course any physical process like weather is at root just that, it's a physical process. But what is the explicit connection between meteorology and then your training in physics? So how did you end up there by studying black holes of all things?
Well, to be perfectly honest, it's a complete and utter coincidence. I studied, as you say, my PhD was in general relativity theory. At the time when Hawking had just discovered that black holes evaporate. And my PhD supervisor, who was also Stephen Hawking's PhD supervisor some years earlier, Dennis Sharma, very eminent cosmologist, he was kind of both excited but frustrated by Hawking's result. He was excited because it seemed to bring quantum mechanics, gravity, and thermodynamics together in one result. But he was frustrated in the sense that the mathematics underlying Hawking's result was very, I would say, obscure. If you look at Hawking's papers, there's kind of complicated algebraic structures which you evaluate at infinity, and suddenly this black body radiation comes out for the quantum fields. And Sharma just couldn't understand, what's going on here. That suddenly you get this black body spectrum. And he asked me to look into a concept which at the time I'd never heard of, called the principle of maximum entropy production. And the idea was there some way of framing Hawking's result using ideas in nonlinear thermodynamics? And I kind of played around with this for a little bit, but almost got nowhere with it and concluded that it probably wasn't much to do with it. But then a year or two later, when I had almost finished my PhD, and I was thinking about, and in fact, I'd been offered a postdoc position to work with Hawking, but I was kind of having slightly second thoughts, and I just happened to be sharing a room with somebody who knew a kind of world famous climate scientist. And this guy said, well, why don't you just talk to him about climate, you know? And I said, well, you know, I don't know anything about climate, and I don't even know whether the maths that I know is of any relevance to climate. And I kind of just went to talk to this guy, almost feeling it was a waste of time. I mean, why am I wasting my time and his time talking about climate? And I said to him, you know, his name was Raymond Hyde. I said, Professor Hyde, look, I'm sorry, but I've been recommended you by a third colleague. But to be honest, I know nothing about climate. He said, look, don't worry, but let me tell you this paper that I've just received this morning from some Australian climatologists claiming to show how all of the Earth's climate system can be derived from the principle of maximum entropy production. So suddenly this kind of really obscure concept, which I'd never heard of, you know, seemed to kind of potentially link black holes to climate. And it just kind of made me think that, you know, science, the basic kind of workings of science apply to different fields, you know. So if you know about Maxwell's equations or you know, quantum field theory or Schrodinger's equation or anything like that, you end up solving differential equations, which are very similar actually to the equations that you meet in fluid mechanics. And so, in fact, a lot of the techniques, and this idea about non-equilibrium thermodynamics was just one example, they carry over. So, you know, I thought, well, I'll give it a go, because I did want to do something. I felt what I had achieved in my PhD, which was a formulation of gravitational energy momentum, was a little bit, I mean, it was a formal solution. I couldn't really see what use it was for anything. You know, it kind of, I thought, well, do I want to spend the rest of my life doing stuff that only a handful of people are interested in? And this experience with this world famous climate scientist made me realize that actually, you know, I could change fields and see what it was like. I always thought, well, I'll give it a go for 3 years, and if I don't like it, I can always move back into theoretical physics. But actually, I ended up enjoying myself, and I'm actually very happy I made the change, because, you know, I have used a lot of the concepts and maths, particularly in nonlinear. I mean, general relativity is a nonlinear subject, as is fluid mechanics and climate dynamics. So, and of course, you know, chaos theory is underpins a lot of things, and that's kind of fantastically interesting, because it gives rise to a geometry that I feel is still actually underutilized in fundamental physics. So yeah, it was kind of it was a slightly illogical change in some respects, but it's one that I'm happy to have made.
Yeah, you mentioned Dennis Sciama, and then I know that Roger Penrose was also an advisor of yours, and you almost then worked with Hawking. So you really had some tremendous mentors and contacts in the field.
Oh, it was a very exciting, I mean, this was in the 1970s, extremely exciting time to be in relativity. And I met, as you say, Penrose and Hawking, Sciama, and from the US, people like John Wheeler, who was a real, you know, father figure, seminal figure there, and others. So yeah, I know I don't regret my time, but also I don't kind of regret actually having spent most of my life doing stuff that's, I hope, of some use to people.
Yeah. Just curious though, I mean, now Hawking is a total legend. Everybody knows his name. When you turned down that postdoctoral position, was he already that sort of star?
He wasn't perhaps quite such a star in the public's eye. I mean, that sort of came about, I can't actually remember what year his book was published. But, you know, he'd written a very seminal textbook on you know, on using ideas from differential geometry, and basically the kind of singularity theorems that he and Penrose co-discovered, that Penrose got a Nobel Prize for. Incidentally, if Hawking had stayed alive, he always used to say he would never win a Nobel Prize because his work was too theoretical. But actually, I think he would have co-shared it with Penrose had he lived. He was certainly in the academic community a superstar. So no, you're right. I mean, if you're saying was it an easy decision to turn down an offer from Hawking, no, it wasn't an easy decision at all. I agonized about it for weeks and weeks, and it almost did my head in.
Well, before we move on to meteorology proper, I just want to try something out. I mean, you mentioned the maximal entropy of black holes, and black holes are the most highly disordered and chaotic objects in the universe. And I'm wondering if one of the connections to meteorology, and maybe these are two different ways of talking about chaos, but the initial conditions of a system in meteorology are extremely sensitive. And if there's a slight shift there, the later conditions can be totally different. So chaos is extremely important. Is there a connection to black holes in that sense?
There is and there isn't, in the sense that one of the fantastically interesting things about black holes is that, no matter how complex and kind of chaotic the star is, when it collapses into a black hole, essentially only three things characterize the black hole. So essentially only three things are left of the collapsing star, which is its mass, its angular momentum, and its charge.
Right, it has no hair.
Has no hair, that's the no hair theorem. On the other hand, and this is kind of this is really at the heart of a lot of theoretical physics. We don't for sure know the answer to this question, but the thinking is that complexity is still somehow encoded in the singularity at the center of the black hole. I mean, we don't have access to that singularity. All we see are these three parameters, but the idea is if we could go in and kind of probe the microstates of the singularity, we would see all of this complexity and chaotic nature revealed there. So it's a difficult. So I mean, this goes to the question of information loss. When black holes evaporate from Hawking radiation, does that information in the singularity kind of get re-emitted, or is it lost forever? And I think we're still unsure about the answer to that question.
If it's okay with you, I'd actually kind of like to deviate a bit and probe more of your thoughts about information and black holes, because as I mentioned before we spoke, I talked yesterday to Eric Verlinde, who is a string theorist in Holland, and we were talking about holography and how the information contained in a black hole is not, on his view, or on many string theorists' view, it's not encoded in this singularity at the center, but it's encoded in, I guess, Planck area units on the surface area of the black hole. And some string theorists, I think Leonard Susskind is the main name that comes to mind, believe that we live in a holographic universe, and that, and this is moving a bit beyond black holes, but everything we experience in the bulk, the center of the universe, is really a projection from a two-dimensional boundary on the outside of the universe. And I'm wondering, when you think of black holes, do you still have this view inspired by general relativity, where the information really is encoded in the singularity, there is a singularity there, or if this idea of a hologram resonates with you?
Well, you see, I mean, this touches on a number of kind of deeper topics, which you may or may not want to get into. But although I in my day job has been very much in climate, the one area I have put quite a lot of effort into in the last couple of decades actually is trying to understand the meaning behind what's called the experimental violation of Bell's inequality. And I have formed a very definite view on this, which is that, you see, the problem is with Bell's inequality. This is the experiment which won 3 eminent physicists the Nobel Prize this year. So it's an experimentally proven result, but the question is, what does it mean? And it seems to kind of go against Einstein's belief that the world is deterministic, God doesn't play dice, and moreover that the world doesn't have what he called spooky action at a distance, which is usually the word used is non-local. So non-locality or actually indeterminism are both, I think, uncomfortable ideas. I mean, non-locality is certainly a very uncomfortable idea. Now, quantum mechanics itself kind of gets around that because the state vector in quantum mechanics can describe superpositions. So it kind of evades Bell's theorem because it's not really deterministic in the normal sense of the word, or realistic, I think, is the word which most people would use. So I'm very of the view that actually there is another way out of Bell's theorem, which is to do with something called superdeterminism, and it's often ridiculed as implying some ridiculous conspiracy. But I think I've written a paper recently on this in the archive, so people can look at it if they're interested, that actually it reflects the fact that the laws of physics are actually much more holistic. And fractal attractors are a good illustration of a kind of holistic geometry. The point about this is that I think there is a way, for me, this points to a way for a kind of potential successor to quantum mechanics, to quantum theory, and that we shouldn't treat quantum mechanics and quantum theory as kind of inviolate and, almost biblical in its correctness, let's say. Now, the point about this is that most, I think, of the people who, look at the black hole problem from this holographic string theoretic kind of perspective, very much do treat quantum mechanics as a given that is not open to violation. So because I don't believe that personally, and I come to it very much from this Bell theorem perspective, I'm not particularly driven to the holographic principle, or indeed anything that absolutely says all information has to be kind of preserved in an inviolate way. I don't come to that as a principle that absolutely has to be upheld. So I would say I am more of a kind of traditionalist in that respect, that I do see the entropy of the black hole is somehow contained in the micro degrees of freedom at the singularity, and not particularly at the horizon. I mean, the horizon is a very undefined quantity, by the way, locally undefined. I mean, all a horizon is it's the surface that just fails to reach, or where light signals just fail to diverge out to infinity. So if I threw a big rock into the black hole 100 years into the future, that would change where the event horizon is today. So there's no way of knowing where the event horizon is today. It's completely, it's undefined at a local level. So I find it very hard to understand how one can formulate notions of entropy and so on in terms of horizon properties. So it's a long answer, but I'm more of a, I'd say, call it traditional GR person in that respect.
I'm really glad that we went down this route. Is it okay if I pursue it a little farther? Okay, great. Yeah. So yesterday, Eric confirmed exactly what you said, in that he told me string theorists believe the world is fundamentally quantum mechanical. So I can understand how if you are going to deny that premise, it's not going to lead you to holography. I understand. I mean, I know much more about Bell's theorem than I do about superdeterminism as a view. So Bell's theorem rules out local hidden variables, but there are, of course.
Well, you say that. You see, it doesn't. It rules out local hidden variable theories if you make this additional assumption, which is called sometimes called measurement independence. It's sometimes called statistical independence. Sometimes called lambda independence. It goes from different names. And, you know, in the early days, some of the philosophers of physics, Abner Shimoni, I think, was most well known for this, made the comment that, wouldn't this mean if we violated measurement independence? If you like, I can explain exactly what measurement independence is, but we might be going down a rabbit hole that you don't want to go down. But the point is, he said, well, wouldn't that kind of, isn't that like doing a kind of a drug trial where somebody behind the scenes is manipulating, which person gets which drug, so you end up with kind of statistics that aren't somehow reliable. And for some reason, that picture has, that's the picture everybody thinks is what is being implied by if you violate this measurement independence assumption. But I've spent a long time, believe me, thinking about this, particularly in relation to chaos theory and fractal attractors. And I'm totally and utterly convinced that this is not correct, that there's a perfectly sort of sensible, logical, feasible, plausible way of explaining this violation of measurement independence without having to invoke any of these kind of weird conspiracies, as they're called. The point about that is that there is, therefore, a way to understand the violation of Bell inequalities without having to give up on either determinism or locality. I should say, I think Bell himself kind of half understood this, and reading his papers, he was kind of grappling towards this, I think, without quite seeing, what was going on. But, I'm happy to debate this with anyone, but as I say, you may not want to go down this too deeply at this stage.
No, so what I should have said was the conventional view, and I think that this is true, is that Bell's theorem rules out local hidden variables and results if someone still thinks QM is incomplete, if they want to preserve or use hidden variables, it pushes them to adopt something like Bohmian mechanics. But what I wanted to ask you is, because I don't really know much about superdeterminism, I think what comes to mind is that it somehow avoids non-locality by positing that what we see as spooky action at a distance is something that was determined locally but long in the past. And I'm wondering if that is how you would explain it, maybe, and why it suggests that to you that quantum theory is not the final theory, and then we can move on to the primacy of doubt, if that's okay.
Well, you see, I'm struggling to sort of explain this in a way where I don't get involved in technical details, which I don't think will interest people in detail. But for a long time in the past, just to follow my career. So I I moved into weather and climate, you asked me whether the mathematics of general relativity is relevant to weather and climate. The answer is yes, to some extent. But what I discovered, and that's why I've gone back to theoretical physics, in the last few years, not full-time, but part-time, is because the mathematics, and in particular the geometry of chaos theory, which underpins a lot of weather and climate stuff, is super relevant to these questions that we're talking about. The idea of let me just see if I can describe. I mean, a chaotic attractor. You take the equations, they're ordinary like differential equations of chaotic systems, and you run them on a computer, and you look at the behavior of the variables in what's called state space. So the state or the space spanned by the variables. So if there are three variables like there are in Ed Lorentz's kind of prototypical chaos model, the equations trace out this fantastic geometry in the three dimensions of the three variables. And I mean, Lorentz's great insight, which took him a long time to get to, was that this geometry that these equations are tracing out is an example of a fractal, or a kind of what's called a Cantor set sometimes, or a fractal. And the difference between a fractal and a kind of simple Euclidean geometry is that the fractal has structure which persists under a zoom. You can zoom into a fractal and you see more structure, and you zoom in again, you see yet more structure, and so on. Whereas something like a sphere, if you zoom into the surface of a sphere, it just ends up looking boring and flat. So something quite fundamentally different. Now, the idea is, if you imagine a dynamical system that is evolving precisely on one of these attractors, and you imagine freezing it in time, and then you say, well, what would have happened if I changed one of the variables very slightly, keeping the other two variables fixed? What you find is you almost certainly move off the attractor altogether. You move into a little gap in the fractal. So a small mathematical perturbation takes you into one of the gaps. Now, when you're proving Bell's theorem, this is exactly the type of question that you have to ask yourself. You say, Alice and Bob measured a particular pair of particles, and they got definite results, up or down for their measurements. But in order to show that your theory satisfies this Bell inequality, you have to ask the question, what would Alice and Bob have seen if they measured those same particles with different measurement settings? So if Alice changed her measurement setting and Bob kept it fixed. And measurement independence says that, they would have just got another set of results, kind of unrelated to the first results. But if physics operates on this kind of holistic geometry, which is the way I like to think about it, then that counterfactual experiment, the one that they didn't do but they might have done, where Alice measured her particle differently, according to the kind of chaos geometry idea, would lie in a gap in the fractal. So it would be actually mathematically undefined. It's not that they get different results, but that counterfactual experiment that you need to prove Bell's inequality would be actually inconsistent with your laws of physics. Now, just to make one last point, the interesting thing about this idea of fractal geometry is that all points on it are sort of equally important or equally, integral to the geometry. So although it's a deterministic system, it's not that somehow there's an initial condition which is more fundamental than any other point. That's the normal way we think about initial conditions. Say, oh, well, the Big Bang was the fundamental initial condition from which everything else sprung. That's not the way it works with these fractal geometries. In some sense, every point has the same ontological status as every other point. And that's a really it's an unusual conceptual, I think, perspective that it gives you. So it doesn't single out, the Big Bang as being kind of somehow special. All points on the attractor are equally special and important. So anyway, that's my, that's very strongly my view. I wanted to say, by the way, if anyone's particularly interested in the gory details, I've written a paper called Superdeterminism Without Conspiracy, which you can find on the archive in the quantum physics, quant PH section of the archive. And so I go into all the details there if people are interested.
This sort of reasoning you're describing, the counterfactual reasoning with Alice and Bob, it actually reminds me very much of the sort of reasoning in the EPR paper that provoked Gauss' theorem.
That's absolutely right. Every single no-go theorem in quantum mechanics involves counterfactual reasoning. Absolutely every single one. So the status of counterfactual experiments in terms of your theory of physics is absolutely 100% critical. This is the single biggest issue which I want to try and get over. We do the real world, works, things happen. We have a theory which hopefully can explain things that happen. But theories, the very nature of theories is that you can change variables and see what would happen if other things were different. However, it may be, and this is the case, I believe, in quantum physics, that some of those changes that you make, which you might think, why not make the change to a variable? It's perfectly reasonable. But actually, there are constraints, these geometric constraints in state space that say that some perturbations you make to variables that are counterfactual actually violate your laws of physics. And that, for me, is the crucial thing for trying to understand these, all of these quantum no-go theorems. So you're absolutely right. It started with EPR, continues through Bell, everything else, GH said, Wigner's friend, which is a lot of the modern stuff is based on things called Wigner's friend. It just does your head in.
David Deutsch.
If you look at it. Have you come across that? I don't know.
Yeah, it's David Deutsch's thought experiment, right? Or am I?
Well, no, it went back to Wigner. So you have you do a quantum mechanical experiment. Wigner's friend. This is Eugene Wigner, very eminent 1950s, 60s physicist. He had this experiment where his friend was doing a quantum measurement in a box. And the question is, Wigner is outside let's say a box. I mean, let's say a room or something which is completely sort of shielded from the outside. So Wigner's outside the room. And the question is, how do you represent the quantum state of the quantum system plus the friend who has done the measurement? So is that in a superposition as well until Wigner himself opens the door and observes that the friend has observed the quantum state to have gone to one of the measurement eigenstates or a different one? And if you believe that, then you can run into, this is all the latest stuff, you can run into problems that what you believe to be a kind of an unassailable fact of the world is actually observer dependent. Different observers can come up with different conclusions about whether, the value of experimental results. Now that's completely bonkers, right? However, to get to that conclusion, you have to assume this measurement independence, that you can talk about counterfactual experiments. And again, if you don't accept that, which I don't accept that, then that stops you reaching these kind of nonsensical conclusions that, facts of the matter are what we think of as absolute facts of the matter are observer dependent. So it rules that out. As long as you can, if you rule out complete counterfactual definiteness, then you don't have a problem with these crazy no-go theorems. They're not so paradoxical after all.
Well, we could continue talking about quantum mechanics all day, and I'm happy to do that. But I also think we should talk about the primacy of doubt. And you already mentioned Lorentz and the geometry of chaos, and I understand that it underpins the butterfly effect, which has dramatic consequences in our lives everywhere from meteorology to finance to the entire solar system. And I guess what I'm wondering is if you could explain maybe how this emerges out of the n-body problem, which is, I think, where it begins in the primacy of doubt, and then why you find the geometry of chaos to be, as you put it, every bit as significant as relativity or quantum mechanics, which is surprising just because I hadn't heard about it before the book.
Yeah, I mean, of course, this concept of the butterfly effect is not new, and in fact,
it comes from Lorentz, doesn't it?
Well, well, okay. I mean, it actually does go back to probably. I mean, it does go back to Poincaré, Henri Poincaré, French mathematical physicist, who was the one actually who realized that the three-body gravitational problem was chaotic. I'll come back to that, but let me just say, in the 1980s, I think it was, James Glick wrote a very masterful book on chaos. And the words, the butterfly effect, I think was coined by Glick to describe it. I think it was the opening chapter of his book. So, from the 1980s onwards, I mean, people have known about, people, in general, the public has known about this notion of the butterfly effect. And, there have been movies kind of illustrating the concept. The one that comes to mind was the one with Gwyneth Paltrow, I think. I think it was called Sliding Doors or something, and it was based in London. And she was going back to her apartment to see her boyfriend, and the doors of the underground, the metro train, were just shutting, and in one universe, she just squeezed through the doors. And I think in the parallel universe, she just missed the train. So that's the butterfly, whether you got through the doors or didn't get through the doors. But basically, I'm sort of struggling to remember the movie because it was years ago when I first watched it. But the one where she caught the train, she got back to the flat before her partner had got rid of her of the girlfriend that he'd had in bed at the time, illicitly, which led to the relationship breaking up and all sorts of, initially bad and then I think good things happening, as opposed to the universe where she just missed the train and the third girlfriend had actually slipped out of the flat, so she didn't spot her, and that sort of led to a different life. So that's kind of manifestation of the butterfly effect. Small things lead to big things. The reason, though, I wrote about it in the book was less to kind of go over that ground, which I think Glick does as well as anybody. So I was kind of, I did actually, obviously I had to describe some of that thing, but what I really wanted to bring out was something which is less well discussed, which is when you have these chaotic systems where the butterfly effect has an impact. it's not always that that the butterfly actually has a big impact. And I cited the famous poem at the beginning of the book that, you know, for want of a nail, the shoe was lost, and the horseshoe was lost, and for want of a horseshoe, the horse was lost, and for want of the horse, the rider was lost, and then the battle was lost, and kingdom was lost, and everything. Well, of course, the point is that most of the time, when horses lost horseshoe nails, you know, kingdoms weren't lost. It's only sometimes they were. And we see that really over and over again. And it's a feature of, you know, we see it in the economy. You know, the economy kind of goes along very, very nicely for a long time, and everyone's super happy, and inflation is low, and GDP is reasonable, and everything like that. And then suddenly, kind of out of nowhere, we either get a big crash or some, you know, big spike in inflation, you know, which hadn't been predicted. Our health, you know, global health, we get outbreaks of disease in place to place, but by and large, global health has been sort of fairly stable until, of course, a couple of years ago, COVID hit us all. And this actually does go back to Poincaré. And he, you know, the idea that, I mean, what he realized was that we take the motion of the planets around the sun as sort of given clockwork almost. It's something you literally set your clock to because it's so reliable. But what he showed was that from time to time, you can get these periods of extreme instability where small changes could actually lead to something really violent, like, you know, potentially the Earth getting ejected from the solar system. We don't actually think that's likely to happen anytime soon, so shouldn't panic about it. But and this is the point, and the weather is the same. You know, forecasting the weather, a lot of the time it's fairly routine, and we can make good forecasts of exactly what it's going to be like, you know, a week ahead, 10 days ahead. But then suddenly, out of nowhere, a weather event occurs which is completely, you know, unpredicted, even a couple of days into the future. So that's the point I wanted to make in the book, that chaos is more than just things becoming unpredictable. It's about this notion of unpredictability being very intermittent. It's something which, you know, you can get very complacent about with a system like the economy, or maybe even like the solar system, and say, oh yeah, it's very predictable, everything's fine, don't have to worry about anything. And then suddenly it comes along and bites you. And the question is, you know, how can we deal with that situation of intermittent instability? And that's what a lot of the book is about that.
Yeah, and I think that this notion of intermittent instability directly brings us to your work in meteorology, because, as you say, the butterfly effect doesn't always have a huge impact, but sometimes it does. And it doesn't necessarily have to have a huge impact. It could have it can still have, I guess, maybe moderate impacts that we need to take into account. And maybe the first thing I should ask is, why are weather systems chaotic?
Well, there are sort of ingredients that you need for chaos that the weather has. And the two most important ingredients are what's called non-linearity. So non-linearity kind of means that the way systems respond, let's say, to some input, isn't in direct proportion to that input. I mean, I think in the book I used the example of you know, if you won the lottery, if you won $1 million or pounds or something on the lottery, you'd be pretty happy, if not extremely happy. If you won £2 million, you'd obviously be more happy than if you won £1 million, but you probably wouldn't be twice as happy. You might be only 25% happier. I don't know. But pretty much everything in life. Well, let's put it this way: few things in life are linear, where the kind of response is completely proportional to the input. And certainly weather, weather, if you look at the equations, the famous Navier-Stokes equations, which are basically Newton's laws of motion for a fluid, and they describe, how the fluid velocity responds to, gravitational forces or viscous forces or other forces and so on. And you see the equation is not linear in the velocity field. So it's a nonlinear equation. So nonlinearity is one important part of chaos. The other is that it has to have this notion of instability, that, an instability, classic instability is balancing a pencil on its tip. The tiniest air disturbance will move it off its unstable equilibrium. And at least initially, the pencil, the deviation of the top of the pencil from its resting position grows exponentially in time. And weather systems, for example, the low pressure systems that run through the mid latitudes. I mean, in the UK, we get most of our rain comes from these low pressure systems, which have grown across the Atlantic, and they reach kind of maturity by the time they hit the UK. And these systems grow from an instability that is a consequence of the fact that the air to the north is colder than the air to the south. So they kind of draw on a temperature gradient, a north to south, a sort of south. Well, south being warm and north being cold gradient in temperature. And that combined with the rotation of the Earth produces what are called baroclinic instabilities. And these baroclinic instabilities are the weather systems that we see in mid-latitudes. But otherwise, convective clouds, thunderstorm clouds are examples of instabilities where the air, if the vertical temperature gradient is large enough, you can trigger a convective instability. So you have these two basic ingredients, nonlinearity and instability, and that's kind of 90%, if you like, of what underpins chaos theory.
Let me try this on to make sure that I have it right. So because weather systems are so chaotic or so sensitive,
they can be sensitive. They not always are. That's the point. You see, that's the interesting question. When are they super sensitive, and when are they not?
Okay. There's an inherent degree, though, of uncertainty in any prediction, given our limited knowledge of both the initial conditions of the system and then the equations that govern the evolution of a system. Is that right so far?
Yeah.
Okay. Then how does this lead to something that you've worked on called ensemble forecasting? And why is this preferable to making single forecasts?
Well, yes. I mean, this is it. We like to think of weather forecasting as, compared with what they did in the Victorian or earlier times, which was little more than astrology. We like to think of weather forecasting as a scientific discipline. We use Newton's laws of motion. We solve them on a computer, a supercomputer. We have very sophisticated observations of weather these days based on satellite, measurements of infrared or microwave radiation, from which you can back out things like the temperature of the atmosphere as a function of height and the humidity of the atmosphere and things like that. And we have Doppler radar systems to give us wind velocity. So we have a lot of high-tech stuff, which makes it sound super scientific. But a kind of defining characteristic of science is that it should be one should be able to estimate the uncertainty if you're making a prediction, you should be able to estimate the uncertainty in a prediction. I mean, you know, anyone who's gone through any sort of practical science class, you do a laboratory, you know, measurement laboratory experiment where you're measuring something. I mean, you'd probably fail if you put no error bars on your measurements. It's kind of and in a way, yeah. I mean, it's the thing. I mean, you could say that's what distinguishes science from astrology. I mean, why is you know, why should you not believe an astrologer who tells you that you'll meet a tall, dark stranger in the next week, for example? Well, because there's no estimate of uncertainty on that prediction. I mean, that if, you know, so I always tell people if nobody can put error bars in their predictions, you should be very skeptical about it, very cautious, which incidentally plays into a lot of climate change questions as well, which we could come to. But, you know, when I started the field, there was no effort to do this. And it's not kind of because people didn't feel it wasn't important, but because they felt that with their limited resources, they had better ways of using computer time and so on. But I tried to make the argument, well, you know, what we need to do is actually, instead of running our forecast models, you know, once, we run them 50 times, 100 times, and we vary these very slightly uncertain terms in the model, or we vary the uncertain observations of the initial conditions. And this is the point, that when the atmosphere is in a stable, predictable situation, those 50 forecasts will look very similar to one another. And then one can be confident that that is what's going to happen. But conversely, in a situation where you do hit one of these intermittent instabilities, it will manifest itself ahead of time by showing the ensemble, you know, massively diverging, each ensemble member diverging from its partners. And at the very least, this is telling you to be cautious about, you know, about making kind of definite decisions. Anyway, this has, over the years, I mean, this I have to say, I mean, this met some resistance early on, not because people didn't like the idea, but they thought there were better ways of using the computer time than running the model 50 times over. They wanted to see higher resolution models or something else put in. But I think over the years, I think it's now the case that every forecast center in the world runs these ensemble models. And of course, they're the basis for the probability forecast that you will get on your, you know, on your mobile phone these days. If you look up the probability of precipitation or probability of rainfall, it's given, you know, as a percentage. But what I mean, if I could just finish with this comment, the thing that has made me feel most pleased, if you like, about this is that it's given the humanitarian agencies a way of deciding in an objective way whether to send in things like medicines and shelter and food and finance and other things ahead of some potential extreme weather event. So, you know, in the past, you know, people I'm sure will remember a hurricane or a tropical cyclone will hit, or a drought or something for that matter, will hit. And after it's done its damage, the agencies then send in, you know, emergency supplies to help the people stricken by the extreme event. And you might say, well, why didn't they send the stuff in earlier, you know, before the event hit? And the answer was that the forecast, you know, when you had a single forecast, you couldn't be sure whether it was reliable or not. And they weren't so rich. None of these agencies are so rich that they could afford to, you know, spend hundreds of thousands of dollars on an event which may never happen. So the question is, how can they decide when to be confident that they can send in emergency supplies before the event has hit? And the answer is they can use these ensemble forecasts, because they can do a kind of cost-benefit analysis, and they say, okay, we've done the cost-benefit analysis. If the forecast probability exceeds some threshold, could be 70% or something, then it makes sense, it makes economic sense to set, and obviously humanitarian sense, to send in send in food and medicine ahead of time. So it's called anticipatory action. And this has really revolutionized the disaster preparedness, the science of it. And it's something I feel, is a real kind of vindication of this route. It's not just some kind of really abstract, chaos theory kind of mathematical stuff. This is actually affecting people, millions of people around the world on a every year, every month, probably.
Yeah, it's also a good example of where your work might be more impactful than the handful of people reading a dissertation on momentum and energy and general relativity. But
absolutely, yes.
Just as an example, so that we can get a better idea of how this works in practice, what might an unstable set of initial conditions look like from a data perspective? And then what parameters would you be varying then in your forecast to accommodate the uncertainty? And maybe a particular disaster could be helpful.
Well, I think it's actually very difficult to, if you ask me the question, what does an unstable situation look like? I don't think it's very easy to answer that question, actually. In a way, because I've looked at many, let's say hurricane type situations, or tropical cyclones, ranging from very, very predictable a week ahead to something like, I don't know, Katrina or something, which is kind of semi-predictable, but not that terribly well predictable, to others which are completely unpredictable, even whether it goes to the west or goes to the east, completely unpredictable. And it's really very hard, I think, to sort of say, well, it was, this relative instability was due to the wind in a particular region or something like that. It's just that the equations of motion kind of integrate everything together and determine, what's stable and what's unstable. But the thing which changed things around in the UK, at least, was a very remarkable storm. It is back in 1987, and it's sometimes called the Fish Storm, and it was named because the then weather forecaster at the BBC was a guy called Michael Fish, and literally the evening before the storm hit, 6 o'clock in the morning, and literally the night before, Michael Fish was giving the evening weather forecast on the BBC, and basically said, tomorrow's going to be a little bit breezy, but nothing too exceptional. And it was literally the worst storm for like 300 years. And I mean, in today's money, it would, billions and billions of pounds of damage was done, and many people lost their lives because they had no warning of the storm. And that was one of the first cases I looked at, and with this ensemble technique, we did it kind of retrospectively and showed that this was phenomenally unstable in the North Atlantic sector. So in the ensemble, there would have been weather, almost any conceivable type of weather that you might think of, from a very balmy day where nothing much was happening through to hurricane force winds. But if you put it all together, then, with a lead time of a day or two, you can see the probability of hurricane force winds was around 30 or 40%. Now, there's this very famous phrase from, is it My Fair Lady? I always forget this, actually, where it says, in Hampshire, Herefordshire and Hertfordshire, these are counties in England, hurricanes hardly ever happen. So you have to bear in mind the prior probability of a hurricane in southern England is as close to zero as you can imagine. So getting something that's 30 or 40% is like an increase in the likelihood by factors of, I don't know, 1 million or something. So this was a very important storm, and I think it made people realize we've got to take this ensemble system seriously and develop it to the extent that it can be used operationally. And basically by 1992, I think it was, we'd implemented the first ensemble weather forecasting system, and it's become, as I say, used around the world now.
Well, continuing then with this example of the fish storm, I suppose what I'm asking is just what was the instability in the North Atlantic? Like, what are the specific data points that you looked at retrospectively that told you this system is unstable? Well, I'm just trying to learn more about how meteorology works in this sense.
Right. I mean, it is an example of this kind of baroclinic instability I was talking about. But it's specifically linked to a particular interaction of the jet stream with the topography of Greenland, and it kind of causes the jet stream to veer in a particular way and to bring down instabilities in the higher atmosphere down towards the surface. But it's this kind of way in which Greenland affects the jet stream is unstable, and so it's small changes in the wind upstream of Greenland, perhaps over the US eastern seaboard and all that area, can have a big impact on where exactly how the topography of Greenland affects the jet in this situation. But I think what I'm trying to get at here is that, we can, people can do, and people do retrospective analyses, but by and large, what we introduce perturbations to the initial conditions, pretty much everywhere in the atmosphere, and we let the equations of motion do what they do on the computer. So it's not like we're kind of analyzing the structure of the jet stream to see whether it's stable or unstable. We're letting the computer model work that out by introducing these perturbations, because the atmosphere is sort of too complicated to just sort of assume it's all one very simple kind of mechanism.
So you introduce perturbations to the atmosphere, and that accounts for one of the two wings of uncertainty that I think we've discussed. It accounts for our imprecise knowledge of the initial conditions. But beyond differing initial conditions, are there other ways in which stochasticity is introduced to the models, like to account for the imperfect equations, or it's not that the equations are imperfect, but our epistemic position related to them is uncertain? But these equations used to develop the initial conditions, are these also sort of randomized in a sense?
Yes, they are, because the equations themselves are not like, I mentioned the Navier-Stokes equations. I mean, these equations are written down using calculus, so what are called partial differential operators, sort of thing Newton basically introduced. But because they're nonlinear, you have to solve them on a computer, and the Navier-Stokes equations, and indeed the other equations which are used in weather forecasting, they couple together, this nonlinearity couples together large-scale parts of the atmosphere, large-scale circulations in the atmosphere with smaller-scale circulations in the atmosphere, and the smaller scales with yet smaller scales, and so on and so on and so on, down to viscous scales. Now, so those equations are, in a sense, precise. They're deterministic. There's no uncertainty in the equations, but you have to solve the equations on a computer, and the computer is finite. What you do is typically there are different ways of doing this, but the typical way you do it is you sort of divide the atmosphere, and by the way, the oceans as well. These days, weather forecasts are done with what are called coupled ocean atmosphere models. So it's not just the atmosphere alone, it's the ocean too. But you divide the atmosphere and the oceans into little kind of cubes, little kind of finite chunks. How big or small a chunk is depends on how fast or big your computer is. If you have a really, really, really big computer, you can run the atmosphere with very small volumes, grid boxes as they're called. But the point is that within a grid box, in the computer model, within a grid box, the atmosphere is assumed completely homogeneous and unvarying. It just has a single wind velocity, a single temperature, a single humidity, and so on. And that's obviously incorrect, because we see, a turbulent fluid has scales of motion on all scales. So a typical, let's say in a typical, today now, the ensemble forecasts are run with models with about a 10 kilometer horizontal. The horizontal side is about 10 kilometers. So we have to assume that within those 10 kilometers, the atmosphere is homogeneous. That's the approximation which allows you to integrate the equations on a computer. But that introduces uncertainty. That introduces errors and uncertainty. So we now deal with that uncertainty by adding stochastic noise to the equations on those sort of small 10 kilometer type scales. And people sometimes feel this is sort of paradoxical, because the Navier-Stokes equations are deterministic, and yet we end up with stochastic equations. How can that be? Well, it's because the Navier-Stokes equations are highly nonlinear, and they couple all these scales together. And the approximation where you assume that the grid box is completely homogeneous is an idealized assumption. So we do add noise, and that noise is actually quite beneficial. It's turned out to be, extremely interesting. And it's got me interested. This is another kind of whole tangential part of the book, about the role of noise in complex systems. And as a very interesting example, the brain. The brain makes, I believe, constructive and positive use of noise. And the noise arises because the brain, this is one of the paradoxes of life, if you like, that we use these big supercomputers to make weather forecasts and climate change predictions and everything else. The computers take something like 20 megawatts of electrical power to run the models. The human brain processes a similar amount of information, but with 20 watts, so 6 orders of magnitude less, which is a very interesting fact. But a consequence of that is that the brain is a noisy system. But I think the brain makes constructive use of that noise. So anyway, noise and nonlinear systems is a very interesting kind of mixture of concepts. And in a linear world, we just think of noise as a nuisance, and we try to get rid of the noise as much as we can. But in a nonlinear world, and we do live in a nonlinear world, noise can be your friend if you treat it with respect.
You just brought up noise, and I'd like to get right back to that. But first, since I mean, this marks a transition, I suppose, to some of the other content in the Primacy of Doubt. I think I just ought to ask, why did you decide to go from your work in meteorology on uncertainty to tackling all of these other topics like economics, consciousness, creativity, and so on?
A lot of things I do, are not necessarily super logical, but my move into consciousness and creativity actually came straight out of noise, thinking about noise, because having introduced noise into the weather and climate models, and shown that it was beneficial, and it certainly improved the reliability of the forecasts because it had an explicit representation of the uncertainty in the equations, and that helped the probabilistic forecasts become more reliable. But I then started thinking, for years, ever since pretty much the dawn of computing, digital computing at least, it's always been assumed that we want to know the answers exactly. So, if we add 2 and 2, the computer better tell us the answer's 4 and not 3.9 or 4.1. And that's all very well, except that today, with being right at the limit of things like Moore's law and so on, this demand for bit reproducibility in computing systems actually puts an energy overhead on the computer. So I started thinking, well, maybe we should. Maybe there are circumstances where we can relax this a priori constraint on determinism, bit determinism in digital computers, because after all, weather forecasting is an application where the models benefit from noise. So one way of introducing noise would be to turn the voltage down across the transistors. They'd become slightly noisy. Now, I'm not saying all of transistors, but some of the transistors. And you save energy that way. So you could reinvest that energy by doing more calculations. So it raises the question, if you had a computer where you could, for a unit of energy, do, 1,000 2 plus 2s and get 4, or 10,000 2 plus 2s and get a number between 3.9 and 4.1. I mean, what would you rather have? And I was arguing that, at least for weather forecasting, and I can think of a lot of other applications as well, where you actually might prefer more imprecise computations rather than fewer precise computations. But colleagues thought I was completely mad to suggest such a thing, that you'd ever build a computer that wasn't precise and so on. And that's what got me interested in the brain. I was trying to think of, are there physical systems that do this actually in reality? They make constructive use of noise in hardware, not noise in software. The brain doesn't add noise by running pseudo-random number generators. It has noise because it tries to push electric signals along neurons, 80 billion of them, with 20 watts of energy, and you get thermal noise. You might even get quantum decoherent noise as well. So my interest in the brain literally arose from trying to think about systems in the world where there is noise in hardware, and the brain was one example. But I think actually we're kind of slowly moving. Some of the computer manufacturers are sort of slightly moving in this direction. And I think it'll be interesting in the next few years to see whether this really happens.
Speaking of noise, I recently had Daniel Kahneman on the show, and we spoke about his book with Cass Sunstein and Olivier Sibony called Noise, and that book is more concerned with decisions that groups of people might make. Well, that a judge, for instance, might make the same decision or different when confronted with the same choice, he might make different decisions depending on the circumstances. I think it's less concerned with the individual mind than thinking fast and slow is. But how was Danny Kahneman's work in thinking fast and slow useful to you in thinking about how the brain makes use of noise for creativity?
Well, Kahneman, famously introduced this notion of system 1 and system 2 as two kind of modes of sort of cognitive thinking. One mode 2 being very kind of logical and focused. The sort of thing, when somebody asks you to multiply two numbers together, you'd have to pretty much shut down everything you're doing and focus on that one task, multiplying the two numbers together. Whereas system 1 is probably the mode that we operate in most of the time, where we're not focusing on a particular difficult problem, but just kind of, surviving the world. We're walking around, we're looking around, we're perhaps listening to somebody speak or something, but it's a kind of multi-purposing process. So that was the first point. And then the second thing which struck me was that when you read about some of the great discoveries that scientists make, and you ask them, where did you make and how did you make this discovery? The thing that gave you your Nobel Prize, for example. As often as not, if not actually more often than not, it was a kind of an idea which kind of came up out of nowhere when the person was just not particularly concentrating on the problem. I mentioned, two people we've already talked about. I mentioned in the book. One is Henri Poincaré, who worked on this the gravitational three-body problem. His key idea was just stepping on a bus one day, and he kind of, oh my God, yes, where's that kind of idea come from? Roger Penrose was crossing the road, dodging traffic. Just the idea came out of nowhere. And it got me thinking, is there any connection between this and this notion that when we're in mode 1, when we're multitasking, this is likely to be the time, I think, when we're most susceptible to the noise in the brain, because this is where the 20 watts are distributed over the multiple tasks that we're having to do when we're in mode 1, as opposed to the single task, multiply two numbers together. All the energy is focused on that single task. You stop what you're doing, you stop walking, you perhaps close your eyes, you put your hands over your ears so you don't get distracted by noise, and just think, what the hell is 19 times 31 or something like that? So these two are very different. And the noise, if the brain's susceptible to noise, it's going to be when it's in Kahneman's system 1. And that seems to me entirely consistent with, the experience of the Nobel Prize winners, that's when they get their kind of eureka moments. And, but of course, the thing is that once they've had the idea, then the deterministic side, the system 2 side, kind of gets to work on it and, really confirms, that was a good idea. That really does pan out. But of course, it's much easier to check. Once you've had an idea, it's easy to check whether it's a good idea or a lousy idea, but it's always difficult to have the idea in the first place. So it kind of struck me that this is a paradigm of creativity, that we get ideas out of nowhere from the mode one thinking when we are susceptible to noise. And then we confirm that those ideas are good ideas or bad ideas by going into mode two. And I personally think that, this has not been taken up nearly enough in AI research. This as a kind of mode towards creative thought processes, to actually let the AI kind of just almost come up with, if you like, ideas at random, and then have kind of suitable algorithms for determining whether these are useful ideas or not. In mathematics, AI is very good at checking potential proofs. It will tell you whether it's a good proof or a bad proof, but coming up with the idea is not yet something AI systems can do. And I think that's because the people who develop these algorithms probably don't put enough effort into the potential of just pure noise for generating potential ideas. And I think that is the way the human brain works, pretty much.
You said that when we're multitasking is when we're most susceptible to noise, and I can definitely confirm that from my own experience. It's also when we're distracted, when maybe that is the same thing as multitasking, but also when we're free associating, that's when our creativity comes in. But what I'm wondering is where chaos fits into the picture here and enters the system one thinking in the brain that produces this creativity.
Well, okay. Possibly the answer is this. I don't, not 100% sure, but you see, there are, in a way, and I make this point in the book, there are two types of chaos. There's the chaotic model that Lorentz originally discovered in 1963, which just has three variables. It's kind of relatively easy these days to simulate. Well, it's very easy on a modern computer to simulate Lorentz's model. In fact, you often see in just screensavers, they use Lorentz's model as a sort of screensaver because it's pretty trivial to integrate. On the other hand, you have chaotic systems like the Navier-Stokes equations, which are partial differential equations, which have, well, formally an infinite number of degrees of freedom, so obviously much bigger than 3. I call those high dimensional systems, high dimensional chaotic systems. And the reason for introducing noise in a weather forecast model is that the computer is finite, and the computer is trying to represent this infinite dimensional system. So it does it with a finite number of equations plus noise. So the noise is a kind of surrogate for, all the small scale stuff that it can't resolve. And, it could be that that's the way the brain deals with, when it builds a cognitive model of the world. I mean, the world is a complicated, infinite, or for all practical purposes, infinite dimensional system. And, the brain is finite. We have 80 billion neurons. That is a large number, but it's certainly a finite number. And again, the brain, I'm using sort of I'm talking about a part of a human, but I'm using anthropomorphic language to say the brain says to itself, how am I going to represent this infinite dimensional system, which is the world outside me, with my finitely many neurons? And it probably will conclude the best, most accurate way to do that is to represent somehow the dominant structures in an explicit way, and everything that it can't resolve to represent with noise. So I think the way the noise comes about, that will link to chaos, is that noise is a way of emulating in a fairly simple way all those infinitely many degrees of freedom that you can't represent explicitly when your computing system is finite. And in the case of a supercomputer, that's the grid boxes being 10 kilometers or something. In the case of the brain, it's the fact that you've got only 80 billion or so neurons. And so, yeah, I don't know. Does that make sense?
Oh, sorry. It does make sense. And this notion, though, of human creativity, at least on the surface, it appears to contrast directly with another brain and mind adjacent topic that you take on in the book, and that's free will. Because presumably, I mean, if we don't have free will, then there isn't really room for creativity. And granted that, especially when we were talking about quantum mechanics, it became clear that if I understood correctly, that you're committed to a determinist view of the universe. How does everything we've been discussing, I mean, most notably the geometry of chaos, help make sense for you of the puzzle of free will?
Yeah. Well, look, I'm going to give you a partial answer because I don't really claim to completely understand this, but it seems that this goes some way. The issue for me what is difficult about determinism, if you like, is the argument that it lets criminals off the hook. It's the issue about moral responsibility in the world, because the criminal just says, well, I had no choice. What I did, the fact that I killed somebody or I burgled a house or whatever it was determined by the initial conditions at the time of the Big Bang. I mean, I had no option but to do that. So you can't send me to prison because I had no choice. That was what was predetermined that I would do. And I've kind of read a few articles by people who try to, who are kind of avowed determinists, to see how they deal with that conundrum. And I've kind of come to the conclusion that they don't deal with it terribly well. They might say, well, okay, well, the purpose of sending you to jail is not to punish you, but to deter other people from committing the same crime. I mean, that could be a typical... Or to
rehabilitate you, something like that.
Yeah, okay, possibly. But I feel that's somehow unsatisfactory because, do you let Hitler off just because you say, well, it was all determined by the Big Bang? I don't know. My gut feeling about this is that I talked to you earlier that this notion of thinking about dynamical systems which evolve precisely on their attractors. In other words, where the equations, the laws are geometric. This is actually quite a different paradigm to the normal, if you like, one in classical physics, where we specify an initial condition and then we have equations which are kind of differential equations which just map that initial state forward in time. And the point I'm trying to make with this picture of the geometry of the attractor being the fundamental quantity is that it kind of all of the points on the attractor are sort of equal ontological significance. There is no kind of initial condition from which everything else evolves. You have to kind of treat. This is why I'm saying it's a kind of a very holistic picture. And I personally think that this is the way in which fundamental physics has to go, and the whole quantum gravity problem, I think, will ultimately kind of come down to the fact that the laws of physics are much more holistic, and, for example, involve the structure of the large-scale structure of the universe as much as, say, just the very small scale, like the Planck scale or whatever. But in terms of free will, I mean, what it means is that the argument that, oh, well, the Big Bang made me do it, this is not a valid argument, because you're appealing to the Big Bang as if it's some special initial state. And in fact, I would say in this context, there's something kind of quite interesting and self-referential in some sense, because I would say that on the one hand, the attractor geometry provides the laws of physics, which determines what individuals do. But equally, what individuals do determines the geometry of the attractor. So there's a kind of a bit of a self-referential loop. And that's exactly the sort of thing, that we see in Gödel's theorem and lots of other really interesting deep theorems in mathematics. So I'm not giving you a very complete answer here, but my feeling is I am personally a believer in determinism, not least because I think stochasticity is, in practice, noise is very important. It's important in weather and climate models. It's important in the brain. So at a kind of practical level, noise is important. But at a fundamental level, if you're really going back to absolute fundamentals, I think noise and stochasticity make no sense whatsoever. And I think ultimately the world has to be deterministic, because I can't see anything else making any sense. But the one problem is with this, I think, the moral responsibility problem. If I believed that the Big Bang was somehow a preferred state and not just one of many equally ontologically equal states on the attractor, then I would actually have trouble with determinism because of this problem of moral responsibility. But I think that treating the attractor geometry as the fundamental issue somewhat diffuses that argument, because one can no longer appeal to the Big Bang as somehow it was special and preferred over all the other states. I need to develop this argument a bit more. I mean, I kind of raised it towards the end of the book. It is a bit speculative, but the more I think about it, the more I feel it's potentially a very deep issue that I'd like to kind of explore a bit more.
So you're a believer in determinism, and then what we refer to as noise and stochasticity are just a combination of the sensitivity of systems to initial conditions, which we can describe mathematically, but it's a combination of this and then our epistemic stance toward them, and that we just don't know enough about them. So we can't get enough information about the initial conditions of a sufficiently complex system, and that results in what we perceive as stochasticity.
Yes, that's exactly right, and the fact that, as I say, we can generate. We can generate stochasticity or effective stochasticity very cheaply. And in fact, we can generate, as I was saying, you can generate it in a computer by turning the voltage down across transistors. So you can generate it at negative energy. So it's a resource that doesn't cost anything. And in fact, not only does it not cost anything, you will actually get back some of the energy that you thought you'd utilize to do more, perhaps, useful things. So at a practical level, we should be embracing noise and stochasticity. But at a fundamental level, I don't think it makes any sense. And I don't think it makes any sense for the following reason, that if you gave me if you gave me a series of numbers, and it doesn't matter how long the series of numbers is, that you say has been generated stochastically by a stochastic system or something, I will tell you how to get exactly those same numbers in a completely deterministic algorithm. So, you can give me as many numbers as you like. There's no way that you can categorically assert that that is the result of a stochastic scheme and not a deterministic scheme. So, as I say, I think it's a sort of an obscure, it's something that just obscures things at a fundamental level. That's why I just can't, it's like in quantum mechanics. We can treat the collapse of the wave function, through the Copenhagen interpretation by some kind of random process, which kind of randomly takes you to one of the, eigenvectors of your measurement operator. That's the standard recipe that people learn when they learn quantum mechanics. And it works fine. I mean, works absolutely fine. It produces all the answers and so on. But it makes no sense at a deep fundamental level. And that's the kind of key behind all of this, to uncover what is the underlying deterministic structure that has the appearance of noise when we formulate things in the Copenhagen way in quantum mechanics.
Well, I'd like to shift gears, because there is one topic that I wanted to make sure that I covered today with the first meteorologist on the podcast. And so we've spoken a lot about weather prediction and forecasts in the relative short term, the sorts of forecasts that someone might make at the weather station. But how does everything we discussed about chaos and uncertainty relate to long-scale climate change, which is a very charged and very important topic?
Yeah, okay. I mean, the first point to make is that climate change is a different type of prediction problem to a sort of 2 or 3 day or something 5-day weather forecast. And a kind of an analogy I sometimes use, and I think it's not too bad an analogy actually, is to let's imagine, I don't know, for the sake of argument, it's December the 21st, so that's the winter solstice, and let's say we're in London or something, you ask me what the weather's going to be like in a couple of days, and I can look at the weather app and give you a rough idea. You might ask me what the weather's going to be like a month from now, and I would be probably very uncertain, probably unwilling to give you any very definite forecast. But if you ask me what the weather's going to be like six months from now, I will say, well, it's almost certainly going to be warmer than it is today, because in 6 months' time, it'll be the summer solstice. And every day after the 21st of December, the sun gets a little bit higher in the sky, and it warms, the air a bit more. And, that's now, of course, we get periods when maybe in February we'll get a cold snap and the temperatures will kind of push back again. But by and large, you can say over 6 months, be pretty damn sure it's getting warmer. And there kind of, it's not, chaos is still happening, but you've got this big external factor, which is the sun, and the fact the sun is getting higher in the sky every day. And this is the sort of external forcing that changes the climate through the year, the annual cycle, in a relatively deterministic way. And I say relatively, I mean, obviously in certainly British summers, we can get some pretty damn cool days when the weather doesn't behave. But by and large, on average, in a statistical way, it would be there's no doubt that summers are warmer than winters. I guess in parts of the United States that would be even more clear. So climate change is sort of a bit like that. It's a bit like the sun getting higher every day, but it's that the carbon dioxide concentration in the atmosphere is getting a little bit larger every day due to our emissions of carbon dioxide. Now, the difference with the sun, the annual cycle, is that this effect is not is kind of smaller on the day-to-day change in the altitude of the sun compared to the amounts of extra CO2, the sun effect is much larger. So we're looking at a kind of relatively small effect, but it's accumulating. Day on day, it's accumulating. Year on year, it's accumulating. Decade on decade, it's accumulating. So we can certainly talk about the statistics of weather, which is basically what climate is, changing in a kind of systematic way as a result of our emissions of carbon dioxide. So people that say, oh, well, because you can't trust a weather forecast more than, a week or two in the future, we can't possibly trust a climate change forecast a century into the future. They're just misunderstanding the nature of the prediction problem. And the prediction problem is much more like, trying to estimate the effect of the sun going up a little bit every day in terms of the statistics of weather between December to February and June to August or something. So that's the first point. But having said that, there are uncertainties about climate change, and the basic physics of climate change is actually not uncertain. So the fact that carbon dioxide is a greenhouse gas and that's warming the planet is kind of pretty. It's 19th century physics. It was well understood then. It's well understood now. So that is not an issue. The issue around climate change is that there are various feedbacks which amplify. Now, you see, I said in the book, and actually one or two reviews from very climate sensitive people kind of criticized me for this, but I said in the book that if carbon dioxide was the only thing we needed to worry about, a doubling of carbon dioxide would only warm the planet by a degree or so, and that would take. I mean, we won't have doubled carbon dioxide from its pre-industrial values till I don't know, actually, certainly to the end, by the end of this, probably into the next century, I should think. And would we bother with one? I mean, I personally, I don't think climate change would be that much of a big deal. Now, some people argue with me about this, but I don't think, if we said, well, we're going to warm by 1 degree over the next 100 and something years, I don't think that would be. It wouldn't be the urgent concern it is. So what makes it an urgent concern is that there are other things which amplify the signal, and a kind of a relatively simple example is water vapor. So water vapor, gaseous form of water, is a greenhouse gas, and as you warm the air, the air can hold more. I'm speaking slightly loosely now, but the air can hold more water vapor. So it becomes more humid on average, and that kind of amplifies the effect of our CO2 emissions. Another quite well-known example is the effect of melting of ice, for example, over the Arctic, because the ice reflects sunlight back to space. If you start melting it, the sunlight gets absorbed by the darker water below, and that warms up the ocean. But as I say in the book, the single biggest uncertainty in climate change, and really the one that is going to make the difference between it being a kind of existential threat for humans and just being a kind of an inconvenience, I mean, a big inconvenience, but not an existential inconvenience, is what happens to clouds, so the liquid form of water, or liquid or ice. And that can go either way. Depending on the altitude of the clouds, and whether they're increasing at low levels or increasing at high levels, their effect can be to damp climate change or to amplify climate change. Now, most of the models, unfortunately, suggest that clouds will amplify the climate change, so making it worse. And that really is what, for me, is the thing which I think, causes us to say we've got to try and solve this problem, because if it's the amplifier and it takes us up to levels of warming that are 3 degrees or more above pre-industrial, then we're looking at levels of climate change which will be awful for large parts of humanity. Maybe not so much for me in the UK, but people in the Middle East and parts of Africa, South America, Central America, Central Asia could be unbelievably hellish. It could be actually levels where the human body can't actually survive anymore. So it all becomes a matter of judgment. Is the level of risk high enough to warrant taking action? I personally think it is, but I do in the book try to make the point that there are two separate issues. One is the issue of what does the science say? And I think we have to be, honest and say there are still big uncertainties about the science, and in particular the role of the water cycle and the clouds and stuff like that. We have a poor understanding of that aspect of climate change. But all the models suggest, and the models are plausibly correct. When I say all the models, most of the models suggest, and they're plausibly correct, that clouds will amplify the climate change signal, and that's what's a matter of concern. I'd personally like to see a lot more, research done on this problem, and I think it's the sort of problem that would be best tackled by an international center, something like a CERN for climate change. I've sort of argued for this for many years, actually. Climate change is such a kind of globally important problem. We ought to be tackling it at a much more global level. But, at the end of the day, because you can take the science output, you can take the output from the models, but at the end of the day, you have to make a judgment. And when I say you have to, I mean individuals maybe, and certainly politicians have to make a judgment. Is the risk of something which is clearly going to be disastrous for humanity, is that risk high enough that it's worth, changing our economy to a zero carbon economy and so on and so forth? And of course, that question is not a pure scientific question. It involves value judgments. It involves questions about how difficult it is to wean us off fossil fuels, and what are the costs, what are the benefits, and so on. I kind of feel this is where actually although I said this is not at a science level, this is not the same as weather forecasting, but there is a good parallel. We talked about ensembles in weather forecasting. So, for example, you want to go on a hike, I don't know, in the afternoon, let's say, and you look up is it going to rain or not? And let's say it says there's a 20% chance it's going to rain. So the question is, do you pack your waterproof gear? Okay, so if you don't pack your waterproof gear, then there's clearly a risk that it will rain, and you're wearing a t-shirt and shorts or something. You'll get completely soaked. It'll be extremely uncomfortable. You might start to feel cold because you're wet. On the other hand, to pack your waterproof gear, you've got to stick them in a backpack, and it's weighing something, and it's a bit inconvenient, and and there's only a 20% chance anyway. So what do you do? Well, it's not a science question. Deciding whether you're going to bring your waterproof gear or not is not a science question. The science question is, what is the probability of rain? 20%. You have to make your value judgments about how much the discomfort of being soaked compares with the inconvenience of carrying heavy waterproofs in a backpack or something. It's similar for climate change, but it's much more serious. We have probabilities of reaching 3 degrees, 4 degrees, and so on. But the question of whether it's worth doing something about it involves value judgments. And so in the book, I try to separate out these two issues. I have separate chapters, one on the science of climate change and one on the sort of factors that you have to think about when you're making this judgment about, are the probabilities high enough? And I deliberately chose them as having separate chapters to make the point that one is about science and one, in a sense, is not about science. It's about how to use science, but putting in value judgments. And I personally feel it is worth, in fact, I think it's almost a no-brainer that we should take action to avoid these risks. But I say that I'm saying that partly as a scientist, but partly just as a human being living on the planet. I mean, not with any particular expertise, but just knowing a bit about the probabilities and the costs and the damages and so on. But I feel when I go onto YouTube and I don't know, see people focusing on minutiae of the science, I kind of feel they're missing the big picture. And the big picture is there is demonstrably a risk of, very serious levels of climate change. I mean, we don't know for certain, but there's demonstrably a risk. I mean, there's no question whatsoever. There is a risk. But the question is that risk high enough that it's worth to take action? And I feel by kind of going into the minutiae of the uncertainties in science, we're kind of missing that big picture. Because just think about it in life. When do you ever make decisions in life knowing absolutely what the future is going to be like? You never do. You always have to make decisions where things are uncertain. And climate change is no different to that. It's not the case that with complete certainty we're heading into an existential catastrophe. And similarly, it's not the case that we are unquestionably, the climate change is a kind of a minor kind of perturbation of no significance. We have to deal with the problem probabilistically, but out of those probabilities make informed decisions about what is the best to make, what is the best decision to make. So
everything you've said sounds extremely well reasoned to me. And just to sum up, the disastrousness of climate change, as you see it, probably hinges on the behavior of clouds, which we don't understand well enough, but most models suggest the outcome will not be favorable. And your appraisal of the evidence is that the risk is high enough to motivate action. So then the last thing that I want to ask before we finish is just what action would it motivate? What are the main options? Is geoengineering one of them? Just cutting carbon emissions? What could actually prevent the potential disastrous outcomes of most models?
Well, the problem with geoengineering, so there is one potential route to geoengineering, which is you spray the stratosphere with aerosols, which would reflect the sunlight back to space. But the problem with that is, again, because of the complexities of climate, we're not completely sure that might not do more harm than good. We might end up shutting off the monsoon circulations, which would, end up with billions of people not having enough food, or we might end up, shutting off the moisture supply to the rainforests, which would then lead them to be a major source of carbon. So we end up going backwards. So I'm not at all a fan of geoengineering, although I think it's something we have to do research on to understand it better, but I don't think that's a solution. I personally feel, again, this is my own view, that we need to embrace all of the technologies that could help us. I'm worried about putting too much into renewable energy because of the problem of intermittency of wind and cloud. For example, in the UK, we're certainly putting there's a lot of development of wind turbines in the North Sea, and there are plans for more out in the Atlantic and so on. And we're certainly building up a lot of solar capability. But we get periods of weeks or longer where the wind hardly blows at all. You get these big anticyclones forming over the UK. Again, one of the uncertainties about climate change is we don't know actually whether these might become more frequent in the future, in 50 years from now, which would, and given that we're moving to an economy where more and more of the energy we need for, transport, for heating, for industry and so on, is coming from electricity, then I think being overly dependent on wind and solar, I think, is a risky solution. So I'm personally somebody who's in favor of, for example, nuclear, new generation nuclear. I'm particularly keen on the so-called thorium reactors, which there's a lot of interest. In fact, China is building a prototype, which have a lot of advantages. But, I think we need, and I personally would like to see, more development of carbon capture. I think I don't particularly see why we should stop burning gas and so on if we can capture the carbon in a reasonably economic way. So some of these things like carbon capture and nuclear are not well considered by some environmentalists. But my own feeling is that this is such an important and urgent problem that we shouldn't let ideology get too much in the way, and we should embrace all of the technologies that we can to solve this problem. And if carbon capture and nuclear are part of that, then I think we should invest in that too.
Well, we've covered a number of topics, and it was really great to be able to bounce around. I'd definitely love to talk with you again, and maybe another physicist, in more depth about quantum mechanics, determinism, and cosmology. But for now, thanks so much for having this conversation with me, Tim.
It's been a pleasure. Thank you very much indeed.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.